So good afternoon all of you. I welcome you on behalf of IISc-SIAM chapter. SIAM stands for Society for Industrial and Applied Mathematics. It is an international organization with a mission to build cooperation between mathematics and the areas of science and technology through publications, research and community by the promotion of applied mathematics. It was founded in Philadelphia in the year 1951 by a small group of applied mathematicians. Presently, there are more than 14,000 members, which include engineers, scientists, industrial, and academic mathematicians. To speak about SIAM chapters, student chapters of SIAM are formed by one or more colleges or universities for the promotion of SIAM activities. There are presently more than 169 chapters across the globe. In India, presently there are 5 SIAM chapters, out of which Indian Institute of Science IISc holds one of the chapters. IISc-SIAM chapter was formed in February 2015. IISc has more than 30 plus departments, including interdisciplinary and research centers. To speak a few words about IISc-SIAM chapter. So far, we had organized student lecture series where research students, be it undergrad, masters, or PhD or research associate, where they speak about their research. We have also organized faculty lecture series where faculty members of various divisions and departments have shared about their work. So far, we had also organized various workshops on Mathematica and Python, and these were very popular and attended by more than 100 plus members across the campus. And we also had members from ICTS, NCBS, NIAS, etc. So far, we had also organized 2 theme events. One of the first theme event was to celebrate Srinivas Ramanujan's birth anniversary, and the next theme event was on imaging sciences in biology. Presently, IISc-SIAM chapter is headed by Professor T. Srinivas, and these are some of the office bearers. So we will request more members across IISc to join IISc-SIAM chapter as executive committee member. We are expanding our execom members. So if you're interested, please write to us. And as our next activity, we are bringing out our first newsletter. So if anybody wants to submit their articles, please submit your articles by the end of this month to iisc.siam chapter. And this is our IISc-SIAM chapter's logo. So if you're interested, please write to us, whether you are interested to know about our future activities or what kind of activities you would like to have from our side. Please write to this email ID. And now I request Dr. Rajneesh to share his screen. So today Dr. Rajneesh will be speaking on mathematical physics and machine intelligence handshake, a peep into the future of Industry 4.0. Dr. Rajneesh is a visual mathematics evangelist, digital and emerging technology lead, and aerospace scientist. He has 13 plus years of applied research experience in aerospace, mechanical sciences, and machine intelligence research and development with a focus on product development. He is passionate about research and technology and impacting society. Dr. Rajneesh has authored 23 research articles. He did his MS research and doctorate in aerospace engineering from Indian Institute of Science, Bangalore in 2014, followed by his first postdoctorate in applied mathematics and aerospace engineering from IISc Bangalore. He has designed and developed an intelligent trailing edge flap for helicopter vibration alleviation and transferred the technology to HAL with CRL4+. Dr. Malik started his industrial R&D career in John Deere Technology Center as design engineer in 2008 after his BTech in mechanical engineering. Later, he pursued his passion for aerospace and applied mathematics and joined Rolls-Royce Jet Engines division in 2015. He has served as an executive committee member in the IISc-IEEE student chapter. He is also the founding president of this IISc-SIAM chapter and American Helicopter Society International chapter at IISc. He delivers public lectures and keynote talks and likes to mentor budding scientists and engineers. He was the panelist and keynote speaker at IIT Madras Conclave on artificial intelligence in engineering in 2019. Dr. Malik was the cluster lead and invited panelist by Government of India in the Global DiveHub Summit in the Aerospace Technologies Vertical and Horizontals in 2020. He is also an alumnus of MIT Professional Education and did specialization in digital programs from MIT Cambridge, USA. Dr. Malik did his second postdoctorate in data-driven research in aerospace engineering in IISc Bangalore in 2001. Currently, he is serving in the Thapar Institute as an assistant professor in the mechanical engineering department and heads the AIMS research group. He is also writing his book on visual mathematics for scientists and engineers. Let us all welcome Dr. Rajneesh and let us all move towards his talk. Thank you.
Thanks a lot, Dave. I'm audible?
Yes, yes.
Right. So very good evening to everybody, and good morning to the people in the other continents, and good evening to the Singapore and other audience if they are available here. So so today's topic, in line with the Society for Industrial and Applied Mathematics. So it is a wonderful opportunity to deliver a talk to the august audience who are mathematically, aware as well as excited. And we all share the same level of excitement. But today, we would like to take the journey even forward together by taking the different fields and combining them together. So that's why I have given the title of the talk as a mathematical physics and machine intelligence handshake, right? So a couple of my own industrial experience in the John Deere and Rolls-Royce. So that I would like to share with you from the perspective of machine intelligence. So I deliberately chose this word machine intelligence, and this is the word which we all generally works with in the mechanical sciences domain, unlike the artificial intelligence, which is more towards on the cognitive side. So I don't work on the cognitive side of it, but I use and try to make machines intelligent. And this is the common terminology which the people such as father of AI, commonly known as a father of AI, Professor Jeffrey Hinton and others, they also refer in their own literature, which is publicly available. So, and on this particular slide, you can see that at the bottom left corner, this one particular cartoon, which I call as a knowledge triangle. So this one is my own creation during my Rolls-Royce days. And so we'll talk about that also in brief detail. This will be much relevant to the people who would like to have a foray in the area of machine intelligence and who are right now in the mechanical sciences research groups in the different universities or alike. So let's formally start. So the talk is going to be divided in three parts. So the first part, generally, I would like to start with the motivation that why we should enter into this area. Is it just because it is talk of the town, or is there something really significant and we can look into from a strategy perspective that how industries are looking at, how really educational research, academic research is looking into it, and what is the future when we talk in particularly from the perspective of mechanical and aerospace sciences, which is my domain as well. The second part of the talk will be about the applications of machine intelligence in mechanical and aerospace sciences. So here, when I keep on talking about mechanical sciences, I refer to all the three predominant domains like mechanical engineering, aerospace engineering, and civil engineering. But certainly the scope is much, much wider, right? Wherever we have the mathematical equations, which are interlacing with the physics, right? So there we are going to definitely have a common handshake. That's what we are going to briefly discuss today. So in the second part of the talk, I'll talk about couple of case studies and also demonstrations, from the public domain, which I have, gathered during my own research work and the literature survey. So in particularly, we'll briefly talk about AI in design, all right? And then we will get into the machine vision work. And unlike the computer vision, as I said, so the focused approach is more towards about mechanical and aerospace sciences, wherever we have the tangible level of products with us. So how we can make them intelligent. So the machine vision is one of the more, proliferating area where of research, especially the industrial research, and a couple of billions of pounds of projects are already underway and successfully delivered, and as part of machine vision. We'll discuss briefly about that. And then certainly on the augmented reality and the mixed reality, a little bit of the work which has been done by a couple of my interns during my industrial research days. And briefly, we'll talk about the data visualization from a totally different perspective. This is very close to me because this data visualization is all about how you present your data, and this is extremely critical. And it's extremely critical for research paper, archival publications perspective, also from when we have to fetch the funding from the government agencies, geared funding from the different international bodies, and also, when we have to make up a story and present it to the stakeholders in the startup and equivalent type of businesses, that is even going to be even more stronger, a portfolio we have to build in rather than just showing some pictures or plots, right? The third phase of the talk, I would like to, have a couple of my own recommendations where I would like to discuss that what are the future R&D opportunities ahead us. And in particularly, I'll be talking about the Bayesian statistics and the causal inferences. And as the title of the talk starts from the mathematical physics, and this is the SIAM related audience, so we'll justify, and very briefly, I'll touch upon my own research work from my group on physics-informed neural networks and the Gaussian processes. And we'll also have a small demonstration of the work in the collaboratory from Google, where I'll show you a live demonstration of solving an differential equations, at least a toy problem to begin with on an ordinary differential equation whose analytical or closed form solution we are aware of, and then how we can solve it using the machine intelligence aware algorithms such as physics informed neural networks. And so we'll see that demo, and then one more practical applications on vibration problems, which are day to day we deal with as a mechanical sciences domain, then how to solve those type of problems using neural nets. So let's begin. So, this is a bigger question we always ask to us, and I used to ask to myself, and still I ask that, why should I learn machine intelligence or practice industry 4.0, right? Or I 4.0. So there are many answers, but the most convincing answer, which came out when I was part of the leadership team in Rolls-Royce. So we were making a strategy document, which is talking about 5 year and 10 years and 20 years down the line, vision 5, 10, and 20. So over there, one of the things which came out predominantly is from the two research, the management consulting groups, especially one is Gartner and the other one is McKinsey. So to begin with, I would like to show you that how the behavior changes globally, and that is being captured, and the work has been done as part of a literature survey. Like in academic research, we look for review articles. Similarly, the management consulting organizations like these, like Gartner, they every year they publish their hype cycle, right? So we'll discuss briefly about what is hype cycle, and that is on emerging technologies. So this was published in 2019. And we'll do a quick comparison on the latest hype curve, and then we'll see that what has really changed and how the pace of research in this particular domain of machine intelligence is really coming in the mechanical sciences, and how and why the handshake and the funding is really pouring in that domain, or unlike, or rather, if I have to say, in parallel with the biomedical research globally. So on the x-axis, we have the expectations. On the y-axis, there are 5 phases of this hype curve, right? X-axis is time. It is all divided. This whole curve can be divided into 5 parts. The first one is innovation trigger. Second one is the peak of inflated expectations, then trough of delusionment, slope of enlightenment, followed by a plateau of productivity, right? So in this hype curve, these particular these small dots with different colors represents when we have to look into from a strategy perspective that how many years down the line from today, in this case 2019, that I have to keep into consideration that which are the technologies which are going to come up and where I can really look forward and where we have to put my investment of my human resource and as well as the capital investment, capital expenditure, capex, which are those key technologies. So where the global industry is really all moving towards. So we'll look into this in parallel with the latest one, which is the 2021, because 2022 is going to be launched very soon, right? There is going to be a conference every year by McKinsey where they publish. We'll discuss about that. However, keep your I would like to draw your attention towards a couple of things, like if you can focus here on augmented intelligence, which is this blue dot, this gray dot, as well as a couple of other technologies like transfer learning, which is mentioned over here, and this edge AI and explainable AI. In 2019, these were the things. Now we are going to witness that in the subsequent slides, that where are they leading to and where we have to really look forward in the future, right? Now on this the other half of the slide, you see this work, which is the report. I fetched it from this is one exhibit fetched from the report from McKinsey, again one of the most world-renowned management consulting group globally. So now here we have on the x-axis the current AI adoption, right? We can see the top right corners are the leading sectors, right? And the bottom left are the falling behind sectors, the actual domains, if we have to say the different verticals in the business. So we can see that, right? So the level of focus by the different groups globally, they all started moving towards in the leading sectors, especially they are from the financial services, high tech and telecommunications. We understand this, right? And but when we are looking from the perspective of mechanical sciences, the automotive and assembly, energy and resources, they are equally going towards and moving towards the direction of the leading sectors towards the top right corner, right? So these all gives quite good indicator that what we have to do. Now let's look at quick, forward, and we passed from 2019 to the 2020-21 curve, which is a reflection of 2022, right? Now, in these 2 years, what really happened is, one is the global pandemic was there, but one key thing which emerged quite evidently is, now remember, I was talking about the couple of things like the transfer learning, edge AI, and here sits the GANs, the generative adversarial networks, and a couple of the augmented intelligence. Now look at this particular 2021 hype curve from the Gartner, right? In published last year, in the later half of the last year. Now, again, the key things which are emerging where we have to really focus our energy and where the globally the organizations such as NVIDIA is heavily investing, right? Google, and many other equivalent organizations which are driving the technology front, at least on the software technology, right? And equivalently, the organizations which are on the hardware front as well, organizations such as Tesla, Rolls-Royce, and Boeing, Airbus, they are heavily, especially Airbus from the airframe sectors, and Rolls-Royce from the jet engine manufacturer's perspective, and GE, they all are looking into something known as physics-informed AI. You can see it over here, yeah, this one. So when I talk about mathematical physics, we'll go deeper into that in the later half, third phase of the talk. But in these 2 years, from 2019 to 2021, the key changes is that the level of the adoption of the technology, and when we are looking at that, what technology really we need to bet upon. So those have really not much changed, but they started maturing, and even the newer players in the market have really emerged even stronger. And if you can see that the physics informed AI is like in the domain of 5 to 10 years, the plateau will be reached, the plateau of productivity, not plateau of the product. It's a plateau of productivity. So it means then after 5 to 10 years, it becomes a norm. Like we use mobile phones today, it becomes a norm, unlike 1994, right? So this is what it means. So now we have to start focusing on these type of things, and we can align our research and our postdoc areas. If the audience is from the senior PhD students or the postdocs or the forthcoming academic or industrial research, leadership, which is sitting over here in this audience today, right? Similarly, the generative AI, right, and the equivalent technologies are coming up extremely strongly. So, and these type of quick literature research tells us from a business perspective that how will these technologies is going to impact my business. And then as a research, academic research, we're also going to know that which technologies should we bet, or we have to vouch for. So we have to be relevant, stay relevant in the next coming at least 5 years in these quite agile world. So keeping this context in the picture, that what we are talking about is not just because of the hype of the Western world or just because of any other marketing. It is the talk of the town because it is being adopted by the global organizations by the global governments. There has been a Niti Aayog report on AI in 2019, which is publicly available. We can read that. And some of the DARPA and the DOE reports from the states are also available publicly on the scientific machine learning in particular. That is where the contribution of people and the research groups and the societies such as SIAM can really come in at the forefront. And we'll also discuss, I'll put light on a couple of the works in the later half of the presentation. So quickly, just have just to give a total picture to complete in this context, let's understand what is machine learning and machine intelligence. So machine learning is a term which was coined by Arthur Samuel in 1959, which means the ability to learn without being explicitly programmed, right? So rather than being explicitly programming the machine, we can get our job done, right? So that we can focus more on the innovation side. So as it is known to most of us, and I'm sure to the most of in the audience, we are all well aware, this is the third wave of AI which is going on. This is not like this is the first time the AI, this world has really started adopting. In 1950s, these are the golden years for, when the first conference happened in Dartmouth. So over there, then the AI was really at the peak for almost 2 decades or so. Then there was a winter in the AI winter means it really have witnessed the slump. Then again there was a boom in 1980s. This is the second AI, this is known as AI summer sometimes. So now again, just after the inception of a couple of computer vision algorithms and the work, the seminal work by Professor Jeffrey Hinton and his group from the Google, that all started getting into the third wave of AI, which we all are witnessing. And sometimes we are being deliberately or unknowingly get pushed towards the the work where other people are publishing in the academic research as well related to the AI or deep learning or machine learning. But we are going to discuss briefly today that how you can start working and leveraging the work, which in fact my research group is also started looking into in deeply, combining mathematical physics and the machine intelligence for mechanical sciences. Right. This bottom right cartoon talks about the two key areas. The first one on the left side is the ANI, artificial narrow intelligence, and this is what generally we all work with. Generally, this is what I deal with, the machine intelligence part. the rightmost is AGI, that is artificial general intelligence, or the cognitive intelligence equivalence being developed by the humans. So I don't work on this area, and this is like making actually humanoids, right? Very few people generally works here, but this 1950 conference is all about, can we really go towards making AGI? And still the research is going on since more than 70 years or so. But let me put into very crisp context that the artificial narrow intelligence or machine intelligence is what is the context in this particular talk, and what we generally most of us work with. Now, when we are talking about the industry 4.0 as well, let's understand that how this the machine intelligence have a handshake, coming into the industrial context. So, and what really we all as a research, community can have a handshake with the industry research, so that whenever we all talk about the valley, the deep valley between industry and academia, how we can bridge that, and so that we can align our research and career interests, for a better future. So the industry 1.0 was all about mechanization, when the steam engines and the equivalent level of technology got invented, right? And the industry 2.0 was when we went into mass production with the advent of the invention of electricity. Industry 3.0 was when the PLCs and the computer technology, and the transistors, they all become the common thing, the contemporary. Industry 4.0 is all about the cyber physical system, CPS, Internet of Things, where the networks and we are leveraging the internet and the computing technologies, where the robotics from the industry 3.0, we can start, these machines start talking with each other and have more productivity with extremely optimal results in the production line. And if you can look at it, the organizations such as Airbus and Rolls-Royce, I have witnessed myself, and this was a very fortunate time to see that the actual smart factories or running, right? These are not the buzzwords, but this is actually happening. Already industries are using. Similarly, in India, we have many factories which are already, especially Tatas are leading in that. So they are demonstrating the smart factories and the factories of the future or so. So we'll discuss about that in detail, partially also in the upcoming slides. So a brief overview of this AI continuum and the knowledge triangle. So this is a common question which I used to, observe to be addressed by the PhD students or the postdocs, and equivalently the MTechs, that I would like to be the data scientist or AI scientist, then what should be my career path and how I can become, because right now I'm into mechanical science, engineering, aerospace, or equivalent. So let me quickly tell you one particular way where you can align with your career aspirations. Let's suppose you would like to go to CXO level. Then you have to master the decision sciences, right? The step-by-step approach would be, so let's say you want to go to the CXO, then that's the IQ, your high Q should be I. So then the knowledge triangle path you should follow. If you want to go into become a CTO, Chief Technology Officers, or Chief Finance Officer or equivalent, then the Bayesian thinking you have to master. Unlike the frequentist approach, you have to go into Bayesian statistics. Let's say if you want to go to the chief staff officer or finance officer or equivalent, then your the people in the management domain. Anyways, the IISc, a couple of professors are doing a wonderful research since many decades on the Bayesian research that can be looked into. But explicitly, the behavioral sciences and the behavioral economics can be explored if you really want to go into the CFO level roles. So right now, most of us, we are extremely good in the domain knowledge, right? So if we just focus on that, or generally we get into, when we get in the PhD degrees or equivalent, then we become domain specialist, all right? So with that specialism, so we can generally work with one or two domains or equivalent, right? So when we combine that with applied mathematics, which is core, subject which is being proliferated globally by the CIAM and the society, and the wonderful work done by the IISc-SIAM group in IISc. So then if the group only get to work, the individual get to work only on the applied mathematics or equivalent or pure mathematics, the person becomes a special, a specialist in algorithm development or research scientist or equivalent type of a career role. Now, the third leg is that, let's suppose somebody in the CSA department or equivalent really focuses on the software engineering or scientific computing or equivalent type of technologies, then the person can become a specialism, earn a specialism in these type of domains and can find their careers in scientific computing or either as an app developer or a UI UX developer or equivalent of that. Now, when we combine two domains, such as the domain specialism with the algorithm specialism, then we can have our career journey on the engineering and technology teams in the industrial research groups globally, right? So similarly, when we combine domain knowledge with software engineering and management, then we get into business analyst or a scrum master, right? These are the common question which appears in the interview in IISc or any other institute equivalently. Now, if we combine applied math knowledge with our scientific computing, then we are on the path to become a data engineer or a data scientist. But when we combine all these three, then actually we become the decision scientist. And these are not cooked up terms, my dear friends. I mean, you can look at in the LinkedIn and the jobs over there in India, outside India, in different continents. Right, so decision scientist is the top-notch, leadership type of a CTO type of a role, or to begin with, at least you can become a decision influencer. But remember, this is the key thing which I want to emphasize, and I'll keep on reiterating in the talk as well, that it is not only applied maths or just computer science which is going to give you the optimal results. You have to own the business problem, and that only can be owned if you own your domain specialism. So if you are today, you're working in the area of your respective research in electrical, electronics, aerospace, mechanical, civil, or whatever, equivalently. So you are actually sitting at the gold mine, because with the domain knowledge, you can earn much quicker research path and become highly specialized in decision sciences and become a decision scientist and quickly reach to your career aim. I have seen many people who have a hard time when they don't understand the business problem and they have to rely on understanding the business problem. And sometimes the results are very colorful, right? Or all kind of fancy graphs, but they don't make sense. And the results will be scrapped by the stakeholders. So knowing the business problem and the domain specialism, the domain specialism is only going to help you. Remember that. OK, so the AI continuum is all about when we are talking about the assisted intelligence, the augmented intelligence, and the brief part of that, which was also part there in the hype curve in 2019 by Gartner. We discussed on that, and the autonomous intelligence. So if you can see here, the AI takes over decision making, right? But at the back end, you are programming it. So these all are just programs which you help the machine to utilize the training from the data which is given to you, the machine, which is going to be trained by the algorithm you have fetched, right? So, and always remember, and don't get overwhelmed by any kind of an information online by these different courses on Udemy, Coursera, edX, or in different domains, that the industry research or academic research, or for that matter, any of these domains, if you really want to look into, nobody is looking for the unicorns, right? So the bottom right is the picture of this unicorn. So don't try to be or chase unicorns. Nobody wants unicorns. And by the way, unicorns don't exist, right? So you just first focus on your domain, then combine that with the applied maths. Anyways, in IISc, and equivalent institutions in India, so our mathematics is really, much better. And then, so you just have to focus on the scientific computing path, and then we are good to go. So let me start, with the second phase of the presentation, where we'll be talking about the interlace between machine intelligence, mechanical and aerospace sciences. And here I'm going to start with a couple of demonstrations and the case studies from the research and technology division, right? And I deliberately write R&T, not R&D, because the R&D is when the technology readiness levels, the TRL levels, is from 0 to 2. Right? Generally, these type of R&D works happens in the academic research in the universities. And when we pass on with the interface, the higher TRL levels, so it is from 0 to 9. It's a NASA rating, right? So from 2, or rather from 4 to 6, these are high TRL levels where the industry takes over and the research happens in the industry. That is R&T, research and technology. So a couple of demonstrations I'm going to show you and the case studies. They are from the R&T, TRL levels 4 and beyond. And TR level 8 and 9 is when it goes into implementation and deployment actually in the market. Okay, so look for R&T and try to, as in PhDs, we also develop the MVPs and the prototypes for patents, for research papers in the industry, for prototypes. So they all are considered as minimal viable products in the industry and R&T from TRL ratings. So this is the common chronology or the taxonomy if you follow in your conversations and whenever you are presenting to the industrial research or into the funding agencies. So it's going to be helpful to you as well. Okay. So let's quickly look into that. So to begin with, I'll start with the demonstrations on AI in design. So here, this is a couple of the research work which is going on in parallel, and some of the work which I have done in Rolls-Royce, so I'm not allowed to share, but the equivalent of that which is there in the public domain, so that I'll share with you and try to inspire you that how the mathematics and the machine intelligence, they all are starting interacting and handshaking with each other and in getting influencing the physics-based solutions, and then trying to get more intelligent solutions. And ultimately, the aim is to make machines intelligent and get our work done even faster so that we can focus as humans more on the innovations. So let me start this. This is a video. Okay. Move on. Mm-hmm. So presenter. Oh, okay, sorry. Dave, was it audible? The audio from the
No.
Audio from the video. Is it audible now?
No.
Mm-hmm.
In this paper, we introduced a novel approach.
Is it audible now?
Yes.
All right. So, so this is the work which is done by the Autodesk Research Lab. And this work was published by a couple of researchers from Japan in Autodesk. So what happens is, so you can see that the velocity profiles, right, and the pressure gradients over an automobile. So this is the one particular structure, the plan form equivalent or the topology of the automobile, right? And this particular indicator at the top left is showing us the drag coefficient, the CD, right? Which is also generally these are CFD flows, the computational fluid dynamics results, quite prevalent and known to the aerospace community, right? You just try, and this is a quite comprehensive, computationally exhaustive, right? It is going to take huge amount of resources. Let's understand that how we can leverage the machine intelligence and handshake it to get these physics information and then combine that.
Approach based on machine learning to predict the aerodynamics of free-form 3D objects in real time. This opens a new avenue for interactive design of aerodynamically efficient objects. Traditional CFD solves the Navier-Stokes equation on a detailed mesh and might require hours of computation on a high-performance computer. Given a previously unseen new 3D shape as input, our tool predicts the velocity field around the shape, the pressure field on the shape, and its drag coefficient. Our tool also visualizes the accuracy of the prediction. Here, the width of the needle in the drag coefficient indicator shows the predicted standard deviation of the error falls in this range. Our system is not tight.
Now you can look at it here, and I would like to draw your attention that this particular grid has certain control points, right? So these particular control points, by changing that, you can change the topology of, and then accordingly, whenever we change the topology, obviously the velocity and the pressure gradients are going to change as well, right? And huge amount of computations we need to do, taking into consideration by changing a new topology. Basically, it is changing a new design. It becomes a new variant of the vehicle itself, right? So having a confidence by reducing the time, increasing the accuracy, or at least ensuring the error bound should be in our, minimal residue should be minimal, error bounds should be in the limits. And then, can we really achieve this objective by comparing that with the ground truth, which is coming from the physics, and comparing that with the machine intelligence based results, which we are computing it with the relatively low fidelity models.
To a specific geometric representation of the shape, we can handle typical shape representation such as triangle soup or parametric surfaces. Our workflow starts with the training phase. First, we collect hundreds of shapes and execute CFD computations for each shape. Each input shape is parameterized using our PolyCube mapping approach. The deformation of a PolyCube template to fit the object's shape defines and encodes the input shape as a fixed dimensional vector. Hence, the PolyCube deformation vector is perfectly suited as input for machine learning. We also use the PolyCube to construct a hexahedral grid around the object. Using a Gaussian process.
Now, again, here, now the mathematical intricate, or the, the Bayesian statistics based approach, which is the Gaussian processes, is again invoked here when we want to simulate the physics based high fidelity models with the low fidelity based, models using machine intelligence. The mathematics is always coming, which is your domain specialism, aligning with the applied mathematics. They all are handshaking always. Now just pay heed over here how they are using the Gaussian processes. Again, this is not based on just probabilistic or frequentist approach. This is based on the Bayesian statistics, right?
We infer the velocity or pressure values at the nodes of the hex grid from the training data. From different base representations of the PolyCube, we can parameterize a wide variety of input shapes. Tenfold cross-validation, we achieved an accuracy of around 3.4% in drag coefficient prediction, which is comparable to the accuracy of regular wind tunnel experiments.
This is extremely beautiful result, and quite logical from an engineering analysis. The wind tunnel experiments are extremely expensive, right? But they are the holy grail. At least on 1 or 2 samples we have to do it. But if you are able to get these results in with the low fidelity models equivalently with a similar standard deviation, then this is a big achievement. So that's why this area in AI in design is really hitting the doors.
Here are some of the comparisons with our prediction against the ground truth.
On the left side, we have the machine learning result, and on the right side, we have the actual high fidelity physics based results, which is referred as ground truth. You can see that both of them are comparable, and the errors are quite less.
Using our tool, we designed it.
Okay. Now, so here inherently from the mathematical perspective, it is not only these colorful plots. So, just look into that. As I was iterating earlier, that the Gaussian process regressor is used as an optimizer to ultimately get to the results, which is highly accurate. And this part we are also going to discuss briefly in our third phase of the talk. But this is something where I would say that most of us who are interested in the scientific machine learning should invest your time and energy, right? So certainly the AI in machine design is also hitting the boundaries in the aerospace domain. And now the aerospace airframe manufacturers, Airbus and Boeing, similarly the jet engine manufacturers such as Rolls-Royce, GE, and the Safran, and so they all are aggressively starting utilizing the capabilities of AI, and then already started making their designs and changes in the design so that we can reduce the lead time, or in the MRO, manufacturing, repair, and overall shops, and the turnaround time, so that we can have a positive cash inflow. Right now, let's quickly look into the machine vision. As I was just mentioning, so from the perspective of the mechanical sciences domain, we are not only interested in that, how to make a distinguish between an apple or an orange, or just a cat or a dog, we are more interested in more practical problems which we get into in relevance with machines, and how we can help to get our machines intelligent so that we optimize their lead time, right, or turnaround time in the. So basically machine vision is an automated imaging association. So it defines machine vision encompasses all industrial and non-industrial applications in which a combination of hardware and software provide operational guidance to whom? To devices in the execution of their functions based on the capture and processing of the images. So whatever images, the still image we capture, or the moving image or the video, right? So we can analyze that, the machine can analyze that, and train them. We can train the model at the back end, and then the trained model ultimately can give us the diagnosis and the prognosis that what is actually happening in this particular scenario. Right now, you can see that these are the 6 classes of defects, right? Like crazing, inclusion, patches, pitted surfaces, rolled in, scratches. Some of them you are quite commonly, we are all aware of, and some of these are quite peculiar in a certain type of an industry, right? So the different other machine vision application would be that, we can have a trained model, which we will train with a couple of images, couple of hundreds or thousands of images of these classes of defects, along with a healthy image, right, without defect, and then let the computer and the machine help us to identify with this still images, and capturing a new still images, and tell us, or rather, if I have to say, diagnose that whether this is a crazing, or this is a scratch, or this is an inclusion. And the next level is to go even further on prescriptive, that tell me under diagnosis that how deep it is, what is the depth, what is the localization of it, of the defect, and then is it really, on the probability, that is it really quite dangerous, or can I fly in the case of aerospace industry, or can I really, do the intended function? So there are many applications of machine vision. It can be guidance, it can be identification of the defects, it can be gauging the defects, measuring it, and also inspecting, right? As I said, especially for the MRO applications. So that's how today the contemporary maintenance, repair, and overhaul industry. By the way, like if you take any kind of a business in either in mechanical sciences, manufacturing, aerospace, civil, or equivalent. So most, or also for the software as well, the making a product and selling it is generally going to fetch us a revenue approximately in the domain of 40 to 60%. Rest, generally the numbers like 60 to 70% of the revenue comes from these services. So basically the service industry drives the innovation and the research and the R&D, research and technology in the industrial research, and ultimately this funding is going to come to the university academic research, and that's how it runs. So basically, if you are really giving solutions in the MRO, it means you are helping industry to fetch more revenue in the 70% bracket, and ultimately they can become more innovative. So, and ultimately that money basically comes to the academic research, by the way, but they will be interested in these type of solutions because they are the burning problems, right? And if whosoever are interested, you can also look into these, you know, the GD X-ray. This is a publicly available data set. This is a data set of X-ray images of non-destructive testing of the mechanical systems, mechanical machines, right? So this you can look at it if you're interested. So now let me go into the predictive analytics and show you one demonstration and and the actual result. So this is my own result. So the y-axis I have deliberately masked because I'm not authorized to share in the public. So here you can see that, and this the top subplot shows these blue dots, and every blue dot, single blue dot, is one flight data. Okay, so let's suppose we are having a flight from Delhi to Heathrow in London, right? So this one flight is one blue dot. Now let's say we have these flights which represents the health of the engine, right? So there are certain particular critical parameters which has been identified, which represents the global health of the engine, right? As pressure values at certain stations, or the turbine temperatures at certain stations in the gas turbine. So that can help us to find out the global health of the jet engine. Now, the objective is to find out the remaining useful life and estimate it using different methods, right? This is an active area of research globally since many, many decades. This was the part of the statistical analysis research groups. And in Rolls-Royce, people at least are working on these type of problems since 30 years. Now, I got an opportunity and to inculcate and have a handshake with the research and the machine intelligence and machine learning, based algorithms we can invoke here. Now, we have the problem that, let's say, we have the data only till almost, later half of the October 2011, this raw data, and we would like to predict that when this engine is going to go for the overhaul, right? So generally the health of the engine, the average jet engine is, at least the passenger extra wide body engine, is 30 years. And in those 30 years of a lifespan of an engine, it goes for 3 times in the overhaul shop for complete stripping exercise. Every single part will be, removed, and it will be inspected because it is a critical, affair. If there is a kind of a failure, so then this is a dead weight which is going to come from the 40,000 feet towards the Earth's surface. So in that respect, so at 3 visits happens. And by the way, most of these engines, especially the extra wide body engines, which are on the 787 Dreamliner or A380 or A320 type of planes. So these engines, the organizations such as Rolls-Royce, GE, Safran, or their conglomerates, they don't sell, they lease engines, right? And the cost of the workshop visit, the strip exercises, is all borne by the company, because we are leasing engines, we are not selling these type of engines, right? So these are contracts based by fly-by-hour. So now the business case is, right, the objective is the academic research problem also can be posed as, can I save one shop visit completely? That is one. The second is, can you tell me accurately with a confidence that when this CN line, right, is the line when this trajectory, the blue dots are going to hit, that is the point when the engine definitely needs to go to MRO, the maintenance, repair and overhaul, or we call it hospital visit. So if you can tell a priori in July that, okay, boss, now the engine needs to go to the overhaul visit. So we give the spare engine to the airliners, right? And then the operator is going to give us this engine so that the operation does not get disrupted, because ultimately it's the customer, right? Which is going to ensure that whether they are going to use that airlines, and ultimately airlines are going to ensure that they are going to go with this particular contract, or these are the business cases. The academic research problem here, if I pose, right? So that is, tell me, which algorithm can help us to predict this particular non-linearity which are happening in this scenario for the jet engine prognostics or the remaining useful life prediction, right? So here you can see in the bottom subplot, this is the actual flight data of all those flights, right? These are all blue dots, and they follow this trajectory. And here the black line is the linear projection, and the red curve is the recursive least square method result, which helps us to tell accurately a priori that we are going to have the PDA functions, and then tell us that with the confidence that okay, it's going to give us the spare engine at that time. So this is just the health prediction of one engine, and if we can do that and save one hospital visit, we are going to save that total cost a priori by just giving the spare engine which is already available to us. So we have a good business running, we have solved the problem, and then algorithm which can be scaled up on all those engines, which or rather to the fleet of engines, right? So it becomes at least a couple of millions of pounds saving to the company every year. Okay, so this is the recursive least square method, and a couple of updates which it seeks. And this is what I was talking about, that this is the applied maths and the invoking the domain specialism. We have to understand the domain so that we know the business problem, so that we have the solution pertinent to that problem at hand. And then certainly the applied maths in combining in conjunction with the scientific computing is going to help us to solve the problem in optimal way. So this RLS method basically is based on the extended Kalman filters. So that is a preliminary part of the machine learning. In that way, you can look at it, the whole picture. So let me quickly now just turn the table and go towards the next generation. As in the first phase, I talked about Industry 4.0. Now let's have a quick walk on the Industry 5.0, right? So here is my own picture when I was in Bristol attending and delivering a talk in the defense visit. So here I'm wearing this Microsoft HoloLens 2.0. Now I think, if I'm not wrong, 3.0 is already in the market, right? So this helps us to visualize and merge the two environments, the physical and the virtual environment. So that is the mixed reality solutions, much beyond the much beyond solutions than just VR, the virtual reality, right? So now how the industry is adopting, and then where we have to look at from the mechanical sciences domain, that this is one more emerging area of research where we can really look into to have our career options. Is let's have a Boeing case study where Boeing says that their efficiency really shoots up by 20% when they started leveraging the competencies from the augmented reality, the AR, and their productivity shoots up even by 40%. And the time consumption has been reduced by a very strong margin, right? And the General Electric, GE, quotes that these are public numbers by the GE, by the way, you can refer and cross-check it. So they say is that by 8 to 12%, so 10% margin is extremely positive, result, even in the academic research, but in an industrial research where immediately the monetary benefits can be leveraged, which can be pumped in back into research, are extremely positive. And the maintenance, repair, and overhaul MROs, when they started leveraging the competencies of the AR, their errors reduces by 85%. And here you can see the picture of the jet engine, where an engineer is wearing an AR solution. He's wearing a Google Glass right now, right? There are different solutions and different industries which have already started utilizing it. This is not only in the research phase. Now it is in the very much in the higher TRL levels, right? Higher technology readiness levels. So Airbus definitely from the airframe perspective is at the forefront. Similarly, UTC Aerospace, NASA, Rolls-Royce, they all are using the technologies which are coming from the industry 5.0, right? Now, these are the different spaces. This is the virtual reality. This is the augmented reality, and this is the mixed reality solutions. And so all different organizations, they are leveraging different solutions today. So this is the cartoon which we have seen earlier as well from the industry 4.0 perspective, but the industry 5.0 is already knocking at our doors, right? As part of the even more smarter factories where the the boundaries becomes too fragile. In fact, because of the global pandemic, which all of us have gone through because of unprecedented reasons, that it becomes even more imperative that can we have a solution, a technological solution, where the mechanical sciences industry and the machine intelligence can be leveraged in the mechanical sciences industry, and we should not lag behind. Rather, we should use this, and then even give even more optimal and better solutions, right? So let me show you one particular small video which one of my interns has made. So this is industry 4.0. Now, in the second phase, this is the last phase of the second part of the presentation. And here I would like to show something which is very close to me, which I call the data sinks. It is not the just visual presentation of the plots, in your research paper, or for that matter in the machine intelligence or AI related work. But this, let me show you how we should present the data. And then, by the way, as Dave also mentioned, that one of my work, which I'm interested in, a couple of my students are working, that is on the interactive visualization, which Mathematica is one of the pioneers, but now even further smarter solutions has come up, which is easy to adopt for mechanical sciences people like me and like us. Just like let's try to look into quickly the data of 200 countries, which got assimilated in 200 years in a span of just less than 4 minutes, right? So right now you can, is there any question? Okay. So here you can see the picture of the person. He's late Professor Hans Rosling, and he has written a beautiful book known as Factfulness. You can look into that if you're interested in actually how you should visualize the data. And one of the work which Professor Hans Rosling was presenting in one of the conferences as a part of his research work, that got so impressed. He impressed the audience so much that a couple of people who were present there in the audience, they literally, approached him and bought his software, which he developed, which was a quite preliminary research work from his research group. And the product name is Gapminder, Gapminder, Gapminder. You can look into that. So, but first, let's quickly in this presentation look the world of visual mathematics or visual statistics. Enjoy this one.
Visualization is right at the heart of my own work too. I teach global health. And I know having the data is not enough. I have to show it in ways people both enjoy and understand. Now, I'm going to try something I've never done before. Animating the data in real space, with a bit of technical assistance from the crew.
So this is extremely beautiful. Professor Hans Rosling, what he is going to demonstrate to all of us is in actual real environment in 3D, we are going to witness with the utilization of the cameras and the technology, couple of videography technology, actual seeing the data in the air, like we use different products these days to interact in the air.
First, an axis for health, life expectancy, from 25 years to 75 years. And down here, an axis for wealth, income per person, $400,000, $4,000, and $40,000. So down here is poor and sick, and up here is rich and healthy. Now,
the plot we're going to witness is known as bubble chart, and this is interactive bubble charts, right? And there's a beautiful tool known as D3, data-driven documents, right? That is what we can leverage to create these kind of interactive visualizations for the research purposes and to present it into the public domains, into your presentations, in decision sciences, and as a data scientist.
Show you the world 200 years ago in 1810. Here come all the countries. Europe brown, Asia red, Middle East green, Africa south of Sahara blue, and the Americas yellow. And the size of the country bubbles show the size of the population. And in 1810, it was pretty crowded down there, wasn't it? All countries were sick and poor. Life expectancy were below 40 in all countries. And only UK and the Netherlands were slightly better off, but not much. And now, why start the world? The Industrial Revolution makes countries in Europe and elsewhere move away from the rest.
So this was
but the colonized countries in Asia and Africa, they are stuck down there. And eventually, the Western countries get healthier and healthier. And now we slow down to show the impact of the First World War and the Spanish flu epidemic. What a catastrophe. And now I speed up through the 1920s and the 1930s. And in spite of the Great Depression, Western countries forge on towards greater wealth and health. Japan and some others try to follow, but most countries stay down here. Now, after the tragedies of the Second World War, we stop a bit to look at the world in 1948.
So this was a time around when India got independence in 1947. So now just pay attention, please, that, you know, one of these bubble is representing India, that life expectancy was quite less, earning was quite less. Now this, we are moving, when we got independence, from the bottom left corner to the top right corner. That is right now where
48 was a great year. The war was over, Sweden topped the medal table at the Winter Olympics, and I was born. But the differences between the countries of the world was wider than ever. United States was in the front, Japan was catching up. Brazil was way behind, Iran was getting a little richer from oil, but still had short lives. And the Asian giants, China, India, Pakistan, Bangladesh, and Indonesia, they were still poor and sick down here. But look what is about to happen. Here we go again. In my lifetime, former colonies gained independence, and then finally they started to get healthier and healthier and healthier. And in the 1970s, then countries in Asia and Latin America started to catch up with the Western countries. They became the emerging economies. Some in Africa follows. Some Africans were stuck in civil war and others hit by HIV. And now we can see the world today in the most up-to-date statistics.
So now, I mean, this was a small demonstration to all of you to say and leave you with this message that, you know, this is how you have to really look into that, you know, how to present the data, right? It is not mere just representation of some plots, right? So let me quickly get into the third phase of the presentation, where we are going to talk about the physics-informed neural networks and small demonstration and a code which I have written for all of you. But before that, let me also quickly give to this some of the audience, especially people who are the research staff, you know, the looking for postdocs or who are the PhD students, that what you should really focus on. So the chasing the unicorns, I have definitely mentioned to you that don't try to be a unicorn. Nobody wants that. But certainly you have to learn and master and focus. If I reiterate, focus on your domain specialism. Without domain knowledge, everything breaks down, right? So if you are in the mechanical sciences domain or equivalent and not in the computer science, you are actually in sitting at the gold mine. You are even more stronger and going to be, you know, on the path of the successful linear, you know, trajectory of your career. So rely on the knowledge, brush up your applied mathematics and you know, applied statistics, and then focus on the scientific computing. Choose any one platform, right? Either Python or these are open source tools, obviously, right? Or R or equivalent, right? Or either MATLAB, Mathematica or equivalent, but open source is preferable in the industry today. And then choose any deep learning frameworks such as either PyTorch, which is developed by the Facebook or the Meta now, or the TensorFlow, which is a deep learning framework developed by Google. These both are free of cost open source softwares. Okay. A couple of recommendations that what you should really work on. As I said, the GPR, the Gaussian process regressor, which was demonstrated in the phase 2 in AI in design, right? So they were using the GPR, which is based on Bayesian statistics, right? And these are some of the good literature which you can focus on. These are, as it is said, that a good book is a word of God. So a book by Murphy on probabilistic machine learning and by Professor Gellman. He's known as the father of Bayesian statistics, at least Bayesian data science. So this is a little dense book, but you can certainly look at and start working from Murphy. And then there is one book by, you know, there's one work by BRML, Bayesian Reasoning and Machine Learning by David. So that also you can look into. Again, one more caution that don't rely on correlations only, right? Sometimes, and in fact, there are published research literature which is based on that don't mix correlation with causation. Okay, so And this is a very funny cartoon, and I generally used to give these in the in my talks, that if somebody says that, okay, people who, when they have shaved their heads, the sales also starts going up. So there's a correlation. So take the razor. It doesn't make sense, right? So you have to look for the causation, right? So there are mathematically rigorous framework also. There is known as causation theory, and Professor Julia Pearl is one of the pioneers in the causation theory. And there's a recent book by Professor Pearl, The Book of Why, wonderful literature. You can look into that and master because industries are appreciating. There was an era where, a couple of years back, 3-4 years back at least, the whole community started moving towards explainable AI, right, or XAI, to get rid of from the black box to the gray box area in the AI. But even further now, the mechanical sciences domain, they are not only relying on it is explainable or not. So we should know the cause, why and how these results are coming. This algorithm is throwing me the results. Then because the results are going to be having lots of stakes when we are going to take a call. So the third one is the GPR, the Gaussian process modeling. So this is one of the research area which I'm also interested in, and one of my research groups are working. So the wonderful literature on GPR is by Professor Rasmussen, right? Gaussian process for machine learning, and certainly by Graham Acey. So this is the area which I would like to highlight. Now we can briefly go on a demonstration from my own research work on the mathematical physics, right? And this is one of the latest research article in SIAM, Society for Industrial and Applied Mathematics, by Professor Liu and Professor Kaniadakis. Professor Liu was his PDF student in Brown. And then this area of physics-informed neural network has really came up really quite well. And in fact, as I said earlier, in the Gartner hype curve, the organizations had already started betting on it, and especially organizations such as NVIDIA are aggressively, taking it up seriously, although being a hardware-related organization, but they are extremely started investing heavily on further understanding and making standalone modules for the pins-based products, and then they have their own library known as Modulus, which runs on CUDA. So that also can be looked into. So let's have a quick demonstration over here, and I'll show you my own code where these results are getting generated. But let's say this is the common, fundamental toy problem in the structural dynamics, that we have this 1 degree of freedom system, where this is typically an underdamped system, and the oscillations are going to damp down. And certainly we know that this is the equation of it in the free vibration equation. And we have the initial conditions. We can tune that, right? And then given this is the frequency of the system, square root of k by m. K is the stiffness of the spring, and m is the mass of this bob. And then we know that we have the analytical solution, a closed form solution of this, right? So the question here is, okay, since we have the closed form solutions, can we use the neural networks not just for some kind of fancy hunky-dory type of things, but actually for solving mathematical physics problems, which are all relevant to all of us. And certainly I deliberately chose the simple 1 degree of freedom, simple harmonic motion underdamped system, so whose analytical solution is given to us, so that we can train our network and get the solutions. Because these type of vibration problems, when it becomes multi-degree of freedom systems, they need to be solved by finite element methods or equivalent, and they becomes extraordinarily important as part of in the industrial research as well as academic research, to understand and finally deploy the solutions for the products, be it in the aerospace domain for the vibrations in the fixed wing or rotary wings in the helicopters, or for that matter in the automobile, or in any domain equivalently, okay? Wherever there are vibrations, it can be in biomedical solutions as well. So the second one, this particular work is about, hold on. I'm sorry. So this is this work. Let's say we have an ODE, a simple ordinary differential equation. Now we are going from practical problem to even more mathematically rigorous problems, and we can slowly move towards a partial differential equation of higher orders, right? Let's say this is a simple ODE where again we know the analytical solutions, and then on the left side, so we have the equation, and on the right side, this is a snapshot of the code which we are going to witness it very soon, and these are the results which we are solving it, and here you can see that, and the bottom subplot. So these are the two solutions. One represents the solution of the y1 and the other represents the solution of the y2. And with that just small amount of training data, and these are even more better and elegant solutions, because by giving a couple of we are integrating the equation, the physics which we know, and we have invested heavily in all those decades to know the system's equation, the governing equations, the system dynamics. Now we don't want to throw it out and just becomes data-driven physics, So we want to integrate the physics information by which the planes are flying, and then use the knowledge of machine intelligence, and then have a handshake so that we solve those problems in a more efficient way with a new technology, right? The solution today in front of all of us is the physics informed neural networks, as I've shown that in the 2021 hype curve as well, right? So let me show you quickly a small demo which I have created for you guys. It was also shown to one of my keynote talk to Intel, so yeah, here we have the exact solution, right? This blue curve of those that 1 degree of freedom simple harmonic motion, and then these are the training points, 1, 2, 3, 4, 5, 6. These are the 10 training points. Yeah. And here I'm using the PyTorch framework, right? Deep learning framework from Facebook, the Meta. It is open source and is available to all of us. And this is all coded in Python. That's why the extension is Interactive Python Notebook, right? And I'm using the Google platform, Colab, which is again open source platform for interactive development environment, IDE. So you need, so this is open source. The platform is open source, PyTorch, deep learning and framework, and the scientific language right now I'm using is for scientific programming, scientific machine learning is the Python. So if you can see that all these tools are the open source tools. That's how the industry is right now looking at it, right? And then the academic research is also aggressively looking into the similar domain. Now this is what we know. Okay, now let's look at it at the different training samples, right? If we just use the neural networks with these sparse data information, right? This is the solution the neural network is going to give us. Okay, the exact solution is this gray area, and this dark blue line is the solution from the neural networks. Remember, I have not integrated right now the physics information into that. If I just want to, get the better solution, I need huge amount of data points. That's why the neural networks are generally known to be as data hungry. Now, let's understand and quickly get into what if I capture and integrate the physics, which I am aware of, which I know very well, okay, and then integrate that with the neural networks. So basically what I'm doing is, when I keep on saying that this is a handshake, basically the loss function, ultimately, whatever we get from neural nets. So that loss function, I also take the, the governing equation and integrate that, the residue part of it, right? If I say f of t minus this mx double dot minus cx dot minus kx, so that becomes a residue, and that particular part is epsilon. And if I plug in that epsilon value as a physics loss into the other the loss function, which I am getting it from the neural network, which is basically an optimization problem, by the way. Okay, so then ultimately just look at the solutions now. Okay, this is physics informed neural network. So now with the 6,000 training data steps, so I'm getting the solution closer. With 12,000, it's better, little bit closer. And with 18,000 steps or epochs, then I just approach the final solution. So this is the power. That's how the simple problems such as these can be solved, and where we know the analytical approach from solutions very well. Now, similarly, this one is for the ordinary differential equation. The framework here used is TensorFlow. Again, a demonstration using a different framework. And here you can see those results with a snapshot of that. I have shown it to you in the slides, right? By running it, we can get this. And this is, by the way, extremely fast. And let me show you and run it right away in front of you. Here I install it. OK. And I'm importing the TensorFlow as my framework and importing the appropriate libraries, and then creating a geometry in the time domain. And here I have created a function. Here we are defining that function ODE, okay, with the appropriate boundary conditions. And here these are the initial conditions if they're required. And then we are just running it. So this is a general one because it can solve PDEs as it is. And these are the different layers of the neural networks. And as I said, this is basically the activation function. And here we have the different calling of the optimizers, right? And if you can note, just in front of you in this very, lecture, I'm showing you the live demonstration running on open source Google Colab using the open source deep learning framework, PyTorch and TensorFlow, and again using the open source, industry standard Python language. And that's it. We have the results, and here we are plotting it. How much time it took? 23.32 seconds, right? So my dear friends, I mean, this is what I mean, that now we have to really look into the future. And if you are sitting over here as a domain specialism and getting trained for in IISc, in other equivalent institutions across the world, so you are sitting at the right place. You just need to focus on brush up your maths, which you are, by the way, I'm sure extremely good at. Just brush it up, and then just make yourself extremely confident that you understand the research problem. Now just complement that with the scientific computing, and then you are good to go to become a decision scientist and on the path to become a CXO of your own company. So this is the last one. I got an opportunity to also lead one small group on the quantum computing during my industrial research days in Rolls-Royce. So the quantum computing itself is something which is also started coming up extremely strongly. So some of you who are interested, start looking at and exploring the up to 5 qubits, right, which are quantum bits, is available free of cost by the IBM to all of us, right? I'm sure today also it must be available to all of us, for free of cost. And you can load your quantum data such as and practice on Shor's algorithm or Grover's algorithm to understand how to do the sorting and equivalent type of small quantum level computations on IBM Q quantum computer, right? So this is the picture of the D-Wave systems, which is the most relatively efficient, commercially available to be bought. You can buy your own quantum computer from D-Waves. This is a Canadian company, by the way. Okay, and as I said, the organizations are also started leveraging the competencies of the machine intelligence using what is known as quantum machine intelligence or quantum AI. And so Airbus has their global challenge. You can look into that if you're interested. And certainly Lockheed Martin is also aggressively working in that area. And the last one I will leave you with is the opportunity to integrate the knowledge of your domain specialism, let's say in mechanical sciences, in aerospace or mechanical engineering or equivalent. So the digital twin and the intelligent machines is the future when you're looking for Industry 4.0 or Industry 5.0. So organizations have already have their minimal viable products, MVPs, prototypes, and working prototypes deployed already in the market. So I would say that that's the area where you should work on. So this is a small succinct message I will leave you with. And it's 5:32. So that was till 5:30 I has the time. So make complex easy. And I'm sure as a mathematicians, we all love the complex numbers, complex theory. But as an engineers, our job should be, and it is, to make complex easy. Thank you. I'll open to any other questions and you can reach out to me at these details. Thank you again for giving me the opportunity. Over to you, Dev.
Is there any question? If there is a question, you can unmute yourself and ask. Yes,
Hello.
please go ahead.
Yeah, right. Am I audible?
Your voice is breaking.
Yeah, my network is very there. Hello, am I audible?
Yes, please go ahead.
Yeah.
Yeah, so Rajnish, thanks. Congratulations from the bottom of my heart for a fantastic talk covering various aspects of machine learning. I have just a humble request, if it's possible to share the Python notebooks and all the associated ancillary materials so that we can just look it up again on our own. Is it possible? Just a humble request from my side.
Sure. I mean, I'll share part of it. Yeah, sure. You can reach out to me on the LinkedIn and we can connect and I'll share that. Or I can also discuss that with Dave later on and we can share part of it. Sure.
Yeah, so those who are attending this talk, so I have already mentioned, please leave your email ID in the chat box. We'll reach out to all. Okay. So please just enter your email ID in the chat box. We'll reach out to all.
Thank you. Thanks a lot.
Thanks, Soumya. Any feedback? I'll be more than happy to also know, because now I have turned the tables. I became I've chosen the academic research as well. So if there is anything you any of the audience want to tell me as a constructive criticism, you can tell me here. If it is too much destructive criticism, you can tell me or email me later on individually. But anything to improve, where I can improve or where you want to collaborate or anything of that sort, we can work together. You can let me know.
Yeah, there are many undergrad students in our audience. So any undergrad students would like to make any comment or anything?
Sir, I have one question regarding the application of machine learning in fluid mechanics.
Yeah.
Kind of, sir, what is the role that machine learning can play in fluid mechanics on general, sir? For example, I am currently working on turbulence modeling using machine learning as a kind of key step to form the closure model for ranks based equation. So, sir, in other aspects of fluid mechanics, can we implement this as a tool, machine learning as a tool?
Certainly, a wonderful question. Thanks, Devanjan. So machine learning. So as I said, I mean, always remember, since this is a CM talk and you all are, mathematical enthusiasts and practitioners, so I can tell it even better because this is the audience I can talk freely with. So basically machine learning, if you really, take the peel off, basically it is, to my understanding, it is a three-way approach. The first approach is we need to define the objective function. Right? Obviously, there is a little bit of intricacies around the statistics and the scientific computing, but from mathematics perspective, the first thing is we have to create a objective function, which comes from the domain knowledge. The second is the creating of the cost function, right? And the third one is basically creating an efficient optimizer, which can optimize so that we can get the cost function optimization done. So be it a domain of fluid mechanics, right, or especially in the application of turbulence modeling or equivalent. So there has been a tremendous amount of literature and of work in at least in the last 4 to 5 years. And if I know from back of my hand, there is one professor, and there are many professors, by the way. So Professor, I have also quoted his name in the talk, Professor George Karniadakis from Brown. He's basically a fluid mechanics scientist. And so there has been research work which is working towards on leveraging the competencies of the machine learning and then integrating that with the fluid mechanics. And there has been tremendous success, right? So, and the AI in design demonstration in the second phase of the talk, which I was showing you, the work from the Autodesk research, that itself is a clear demonstration of the integration of the machine intelligence with the physics, which is coming to solve the problem in the domain of fluid mechanics, because we are trying to simulate the ground truth of the pressure fields or the pressure gradients or the velocity profiles. So those are one of the critical outputs which we get it from the CFD, the computational fluid dynamics. If you use either RANS or LED or or Boltzmann's equations or equivalent of that. So basically they are trying to do the same thing, but if you have the different type of data assimilated with you so that you can get a good training model. So certainly you can create all those cost function, objective function, and optimization and get your job done. And there has been lots of literature.
So basically some machine learning is a kind of tool then by using which we can augment our like already existing work or like the kind of work has been going on.
It is an approach by which we can automate most of the contemporary work, not all of the contemporary work, but most of the contemporary work, right? As this area is also emerging quite fast, right? When I say this area, so there is always one of the very strong debate globally going on that is it really machine learning or is it just old wine in a new bottle with a new jargon in the marketing domain? That or is it just statistics, right? So basically, if you see all those kind of confidence, plots, heat charts, and all those numbers, right? This truth tables, these all are very much prevalent since many decades in statistics, right? These are not new. So now when we are talking about the Bayesian machine learning, probabilistic machine learning, all those are all sitting on the very strong framework of statistics. So it is not new. So when you say that, we have to integrate it, yes, it is just a new domain, a new tool where you can automate your contemporary work. If you look at it from that perspective, and also remember that it is basically a smart way, extremely smart way of handling the sparse amount of data, right? If you are doing the physics-based, machine intelligence, then it is a sparse-based analysis. Else it is a, big data, whatever the humongous amount of data we get, and then we want to create a model around that and find out any kind of a hidden information. That is what it is going to help you with these mathematical models, be it linear regression, ridge regression, you name it. All those are mathematical functions. And then we create an optimizers on that. Either it is stochastic gradient descent, Adam optimizer, or these all are just different optimization routines. So to me, I mean, it is basically applied mathematics running smartly on a domain problems using the scientific computing tools, either MATLAB, Mathematica, or Python, or whatever, you name it. That's it. Right?
So how will it be different from the numerical methods or I think the machine learning is fairly different from numerical methods, like
So if I say, so numerical methods is, so basically it's part of it, but machine learning, so whatever data it comes, so we close that loop, right? So that we ensure that the data is getting trained. The machine can train itself on the data. So that is known as active learning or online learning, right? So whatever data comes, the machine learns on that itself. So we can reprogram it. But generally on numerical methods is basically is a mathematical way of solving a mathematical problem using computer, right? Or, or rather before computer, using it by different algorithms. So these all algorithms, when we fetch it and ingest it into the optimization routines of automation, then it is the first step towards machine learning. And then when we close the loop, then that's how we help the machine to learn itself again and again. And when the data comes, the machine learns it. That is online learning. So they all are quite interlinked. So we need not to disengage them. Look it from the lens of mathematics, scientific computing, solving a problem which is coming from your domain. That's it. I think then it is extremely easy and you will have a passion for it and you can relate it relatively quite easily. That's what how I see. Yep.
Thank you, sir.
Hello, sir. I'm Guru Raj. I just wanted one addendum to the question regarding that Autodesk work. Basically, you told like the CFD was solved for different types of models, and using that trained data we used for some new design. So, but in cases where this CFD itself is so highly computationally expensive, so using that as training data, how machine learning adds to, how it is beneficial, sir?
That's a wonderful question.
Because
So,
many cases we are not able to solve even CFD fully. So only I was thinking how.
Right. So basically, that particular research work is all about that. Whenever we have solved the problem using CFD, then we so let's say, so one of the key common problem in the industrial research is that what if, because can you reduce the design cycle time? Let's say actually to design a new vehicle, let's say an automobile itself, the design cycle time, it takes approximately 2 to 10 years, right? It varies a lot. These days it is really getting crunched. But now when any new variant comes, because of the certification agencies and many other security protocols, we have to rerun the tests, all kind of security protocol tests for certification. So that anyways we have to do. So the objective is to reduce the design cycle time, at least, right? If we change any of the variants or any of the design, so can we quickly get the results with the highest level of confidence and accuracy? So today what we do generally when we change the iteration, so the design team talks with the structural analysis team, then with the CFD team, and then again it goes into iteration, then it goes into manufacturing team, and then further other teams gets invoked. So this particular part of the design, talking with structural analysis team and then talking with the computational fluid dynamics team, can we reduce this time? That's an objective. So over there, the Autodesk research, what they did, and as part of the research work, they try to squeeze this particular timeline. So when we have the results, right, from the high fidelity models, and we put that data as a training data, then whatever variant we change, right, a new variant appears, there we need not to retrain it again and again. So there we can have these kind of grids and then get the results of our dependent variables using our low fidelity models. So that is an objective. Although if you really are getting into extremely intricate, computationally expensive exercises, so there, it becomes, that's why these are high fidelity models and it is going to be computationally expensive. But when we have done it once, because we need to give the training data, right? So these models are not going to learn from itself. Basically, if you take it simply, like let's say y is equal to mx plus c, if you want to do a linear regression on a random data. So we need the dependent to compute the dependent variables. We need independent values of the data, right? As I have also shown you on the predictive analytics for the jet engine health monitoring, those blue dots are required. Although every blue dot represents this particular charts, every blue dot is an expensive individual flight data, right? So it is required. So without that, we cannot train, because without that, we don't have a X vector. And then with the X vector, we need to create the X cross X design matrix. And then we want to take X transpose X inverse pre-multiply by X transpose Y. So then we going to get the Y tilde, and that Y tilde is our prediction, right? So we need the training data. So from somewhere we have to get it. If it is not CFD, from the experiments. If it is not experiments, the actual flight data or equivalent. So we need the information, because without X independent value, we cannot predict Y, right?
Right, sir. Understood.
Yeah.
Thank you.
Yeah.
Are there any more questions? So if there are no more questions, then we can just unmute ourselves and give a big round of applause for Dr. Rajneesh.
Thanks a lot, Dave. Thank you for the opportunity. And it was an honor to present to my own colleagues, my own friends, right? The forthcoming future generation leaders and researchers. So my all best wishes to all of you. I'm more than available anytime. And it is even more pleasure to see Professor Srinivas also, along with my own friends who are the leadership, Kunal, Shweta, and a couple of other people. So thank you. Thank you all. And if there is any other particular feedback you would like to share with me, as I said again, so I'll be always available, and you can reach out to me at this particular address. So thank you again, Dave. Thank you.
Thank you.
Shall I leave?